So hello and welcome back to advanced ring theory problem solving sessions, and we were involved in the TIFR PYQs. So in the last lecture we had completed till this problem, and this was the last problem which I had actually proposed as a homework. Nevertheless, we'll start our solution with this very problem. So I'm removing this part. So what is the question saying? Let A be the collection of all tuples alpha beta, integer tuples, such that the roots r1, r2, r3 of p of x, which is a polynomial given to be x cube minus 2x square plus alpha x minus beta, satisfies that r1 cube plus r2 cube plus r3 cube is 0. Now, which of the following statements is correct? So, A is infinite, empty, singleton, and A is finite, but is not empty and not singleton as well. So, the first thing, or rather I would suggest, the first thing which you usually, comes to your mind when you get problems involving roots of polynomials is the Vieta's formula and the Newton formulas for the for the roots and the coefficients. Okay, so let us try to give a solution to this question. So what we'll do is that first we'll sort of abbreviate so that we are notationally good. So what we do is that we denote the roots by Ri and not R1, R2, R3 every time. So the roots are Ri such that I belongs to 1, 2, 3. We are good, right? Now each of these Ri's are roots of the polynomial x cube minus 2x square plus alpha x minus beta. So therefore, for all I, we have Ri cubed is equal to 2 times Ri squared plus alpha Ri, minus alpha Ri plus beta, right? Now if I sum over all these i's, so that implies summation I is equal to 1 to n, Ri cubed is equal to 2 times summation I is equal to 1 to n, Ri squared minus alpha times summation I is equal to 1 to n Ri plus beta, right? No, sorry, plus 3 times beta, because we are going to get 3 betas, right? Now we know what, that from the Vieta's formula, now through the Vieta's formula, you might not know the name of the formula, but I hope you surely know what the formula tells. So it tells that the sum of the roots gives you the coefficient a1 up to a multiplicity of minus 1, right? So now through Vieta's formula, what do we have? We have the first elementary polynomial, which is summation Ri. This comes out to be 2. Okay, so because you have a polynomial of the form x cube plus ax squared plus bx plus c, so this gets hold of the multiplicity of minus 1 to the power 1. This is minus 1 squared and this is minus 1 cubed. So therefore the coefficient bears the sign of minus 1. Okay, fine. Yeah, so I hope what I did is perfectly correct. Yeah, fine. Okay, so next what we typically have is that what is E2? So E2 is the sum over all the products of these, right? So I ranges from 1 to 3 and j ranges from 1 to 3 as well, and then this should surely come out to be alpha, right? Yeah, so the sum of the roots, it actually gives you this very coefficient. I'm extremely sorry for I just misplaced it. So this is minus 1 whole squared. Yeah, fine, we are good at this point, because the polynomial is after all x cube minus 2x squared plus alpha x minus b. So I don't want to mispronounce or miscommunicate anything. The polynomial what we had is x cube minus 2x squared plus alpha x minus beta. I usually stumble upon the first problem because it takes some time to build out the momentum. So this coefficient is so sum of the roots has to be minus of minus 2, which is 2. Yeah, now we are perfectly all right? And now the sum over all the products in pairs of the roots will give you this very coefficient, so it is just alpha. And what more we can say? So finally, if I consider this polynomial, which is the sum of the squares of each of these roots, then by the Newton formula, this comes out to be e1 square minus 2e2. This is a very easy verification. And then this would then come out to be 4 minus 2 times alpha. So I think we have all what we required for this very formula. So we have the value of the summation of Ri cubed, Ri squares, and summation all over Ri's. So therefore, summation Ri cubed should come out to be 2 times 4 minus 2 alpha minus, and what does this give me? So sum over all the roots, it actually gives me 2. So minus 2 times alpha plus 3 times beta. And by the hypothesis, this is 0. So therefore, what we have is 8 minus 4 alpha minus 2 alpha plus 3 beta has to be 0. So this implies, so this is 6 alpha, so I can bring thing outside. So you have 2 times alpha minus beta times 3 is equal to 8. Now alpha and beta are in integers. So alpha and beta are in integers. That surely means that 2 alpha minus beta is an integer, which clearly means that 3 divides 8, which is a contradiction because 3 obviously does not divide 8 in the integers. So therefore, we won't be able to get such a pair alpha or beta. So therefore, it has no solution, so it's empty. Okay, let's move on to the next question. So true or false type question, R x over x to the power 4 plus x squared plus 2023 is an integral domain. Okay, so observe that the best way to solve this very problem is the following. You don't need to check anything whatsoever about this polynomial. The only fact which you should be very clear in your mind is the following. Over R, only irreducible polynomials, or rather I should frame it this way, all irreducible polynomials has degree either 2 or 1. And what is the very typical reason behind that? So if you take any polynomial, suppose ax to the power an x to the power n plus an minus x to the power n minus 1, so on and so forth, till a1x plus a0 is equal to 0, then the roots of this polynomial either lies in C or it lies in R, right? Now, if none of the polynomials are in R, for example, so if it has a root in R, then obviously it will split into a linear factor and a polynomial having a lesser degree, right? We're trying to talk about irreducible polynomials. So if I assume this to be an irreducible polynomial, then it surely cannot have a root in R. So the only possibility is that all the roots must be well in C. And also we know something very interesting, that over real polynomials, complex roots always appear in conjugate pairs. Now if alpha bar, so if alpha is a complex root of this polynomial, alpha bar is also a complex root of this polynomial. And in this case, you can, both alpha and alpha bar are simultaneously the roots of the polynomial x squared minus alpha plus alpha bar x plus alpha alpha bar. Right? So this is well constructed by Vieta's formula itself. So the sum of the roots form the coefficient of the next term immediate to the highest degree, and the product of the roots form the constant term in this particular case. And observe that since alpha is a complex number, alpha plus alpha bar is a real number. Alpha alpha bar is also a real number. So this is a real polynomial, and since alpha alpha bar are roots of this very polynomial, and we constructed out this polynomial from these very roots, what typically follows from here is that this polynomial is a factor of this, right? Something very interesting which we can clearly observe, because this polynomial will surely split into, so if you just bring it over C, if you extend this over C, because after all this is a real polynomial, the real field is itself sitting inside the complex field. So if you view this as a polynomial over C, then it will surely split into x minus alpha times x minus alpha bar times some polynomial, and this is real polynomial. So this quotient has to be a real polynomial as well. So therefore, any polynomial of degree greater than 2 will always split into a linear factor or a quadratic factor, depending on whether it has roots in C or in the real life. So therefore, you cannot have a degree more than 2 irreducible polynomial at all over R. So therefore, this polynomial is surely reducible. And we know that Rx is a PID because R is a field, so it's a PID. And over PID we know that Rx, so if R is any PID, so R mod I is an integral domain if and only if the quotiented ideal is a prime ideal. And since it comes out to be an reducible element, we know over PIDs irreducible elements are equivalent to prime elements. Okay, non-zero prime elements for obvious reasons. So therefore, this cannot be an integral domain. So it's a false statement. Let us move on to the next question. So for a polynomial f of xy in real polynomials with two variables, we define xf to be the collection of all tuples ab such that f evaluated at ab is exactly equal to 1. Then which of the following statements is correct? If f of xy is this given polynomial, then xf is compact, and so on and so forth. So we are actually dealing with the roots of the polynomial f of x minus 1 as a set, where f of xy is given as x square plus 4xy plus 3y square, or x square minus 3xy plus 3y square, x square minus 4xy minus y square. Okay. So these sort of polynomials are what we typically call homogeneous quadratic polynomials. Observe something very clearly. What is xf actually? Let us move on to the next page. So xf is actually f inverse of 1. Okay, and this 1, the element 1, it actually in R is closed, and this at xf it belongs to R2, so it's a Euclidean, so it's under Euclidean topology, and therefore we know, so this implies that xf is compact if and only if xf is closed and bounded. Okay, fine. Now we have something very, a set of very interesting facts about quadratic equations, or rather quadratic polynomials of the form. So the quadratic polynomials involved in this question are primarily of the form ax square plus bxy plus cy square, and these polynomials are basically what we on a general note call homogeneous quadratic forms. Okay, and the set xf which are actually dealing with, so it is the collection of all the points ab such that f at ab is equal to 1. So it just describes a locus. It just describes a locus of this particular quadratic form, and the locus actually these give some conic sections, some conics, which we typically primarily call central conics. Now this conic is bounded if and only if the quadratic form, the given quadratic form is so it has to be positive definite. Yes, yeah, it has to be positive definite, and when it's bounded, so it's actually, it forms an ellipse. Okay, and how do you describe whether a given homogeneous quadratic form is bounded or not? In that case, you require the notion of the discriminant. The discriminant in this particular case will come out to be b square minus 4ac, and for it to be bounded, what you require is that the discriminant is less than 0 and a is greater than 0. One more step which you can actually check whether the quadratic form is positive definite or not, you can actually follow what linear algebra has typically taught you, if you recall. So through a linear algebraic approach, you can associate a symmetric matrix to it, and then you can check whether the matrix, the corresponding matrix, is positive definite or not. But nevertheless, we can easily go through this discriminant format, something very new, probably new to you. And then I will be leaving this exercise here as well to check that which of the options actually satisfies this valid condition. Whichever option satisfies this condition, that has to be the correct option. And I don't know what the correct option is. So let's just move on. So the next question says again a true or false type of a question. So let R be a ring which is Cx mod x squared obtained as the quotient of the polynomial ring Cx by its ideal generated by x square obviously. Let R naught be the multiplicative group of units in this ring. Then there is an injective group homomorphism from Z mod 2Z cross Z mod 2Z into R cross. Okay. So first of all, this group is nothing but the Klein 4 group K4, or also sometimes written as V4. So what I actually need to see is that does R cross, the collection of all units in Cx mod x square, actually contains a subgroup which is isomorphic to V4. Okay. So how can we actually try and check whether it's seemingly possible or not? So suppose you choose an element u, let's say of the form a plus b x, or rather x bar, to be pretty valid with the notation because we are working in a quotient group. Suppose we choose this element in R cross. Okay, now since it's a unit, obviously a has to be non-zero. And what can I say about u squared? Suppose if u is an involution, suppose u is an involution, so its square is 1. So if u is an involution, then we would have a plus bx bar whole squared, which should come out to be a squared plus b squared x bar squared, but x bar squared will be 0. So it's just a squared plus 2 times a times b times x bar. It should be 1. Now if you equate this particular equation, now since we know that Cx mod x squared, this actually has an C basis. This is a 2 degree, a 2-dimensional vector space over C. So it has the basis 1 and x bar. So then what you typically get from here is that, you have a squared to be 1 and you have 2ab to be 0. Okay. Now when can a squared be 1? So a squared be 1 should imply that a is in plus or minus 1. Okay. Now if a is 1 of plus or minus 1 and 2 times a times b is 0, this should immediately imply that b has to be 0. Am I being clear here? Okay. So now what can we say? Now the first thing is that you might ask me a question that why did I choose u as an involution? See, the main motivation behind checking through this is the following fact, is that if V4 is actually embedded in R cross, then we know that V4 consists of the identity element and 3 elements of order 2. So I need to check whether there exists an element of order 2 in R cross or not, and if so, how many are there, to be very specific. Because for V4 to be embedded in R cross, we need at least 3 distinct elements of degree 2, which behaves well under composition or rather multiplication, whatever you want to say it by. Okay, so therefore the elements which are getting mapped to 1 on getting squared, that is the involution elements, so we are getting only 2 possibilities, either 1 or minus 1. So therefore now plus 1 is obviously not an element of order 2, it's rather the identity. So what we have actually seen is that Cx mod x squared cross has only one element of order 2. While for V4 to be embedded in R cross, we had to have three distinct elements of order 2. Therefore, the embedding is not at all possible. So this is the way in which you usually argue in your mind, I would rather say, because in exam you won't be able to construct out such a rigorous solution. Nevertheless, this is a false statement. Let us clearly move on to the next question. Just a second. Okay, so let's come back. So we are given a set of real polynomials as follows. So S is the collection of all real polynomials. P is not constant, and the value of P at origin, the absolute value of P at origin is less than 1. Now if P is such a polynomial, let UP be the collection of all those real values at which the absolute value of P is less than 1? And then which of the following is correct? So then again, what you should be immediately getting into hand is that the set UP, which is defined to be the collection of all those real numbers such that modulus of Px is less than 1, then this is exactly P inverse of the interval -1 to 1. And now obviously P is a polynomial, a non-constant polynomial rather, but nevertheless P is continuous. So P is continuous, -1 to 1 is an open interval and hence it's open. So this implies UP, which is inside R, is an open subset. So it's open. And from the Lindelof theorem in R, which applies, says that any open subset of R uniquely decomposes into countable union of disjoint open connected components. Okay, so any, or rather every open subset of R decomposes into, decomposes uniquely into a countable union of disjoint open connected component. So basically it actually decomposes into disjoint open intervals, and each open interval is a open connected component. Okay, so what are the options? Let us first check this. So then UP is a union of infinitely many disjoint open intervals, union of infinitely many disjoint open intervals, union of finitely many open intervals, and is unbounded. Okay, so this won't work, or this is actually not working. Okay, now first thing which you should be observing very clearly is that Px is a non-constant polynomial. So therefore, since P is non-constant, so that should imply that P has an asymptotic behavior. That is, limit mod x goes to infinity, mod of Px should be infinity. Now, the region P of x less than 1, it is confined to a bounded domain. Confined to a bounded domain, which obviously strictly invalidates D. So this is obviously not correct. Okay. Now what next can I say? Now what is the what should be the topological boundary of UP? So at the boundary of UP, you should be able to get all those particular real numbers at which modulus of P of x is exactly 1. So the boundary of UP is the collection of real numbers such that P of x is equal to 1 or -1. So therefore, what should I say in the following sense? So therefore x is a root of the equations Px -1 equal to 0 or Px plus 1 equal to 0, right? So therefore this boundary, it is actually contained in the collection of all real numbers such that P of alpha -1 equal to 0 union alpha in R such that P of alpha plus 1 is equal to 0. Now observe that each of these sets are finite, because we know that a polynomial equation admits finitely many roots. So therefore UP has finitely many boundary points. So therefore the boundary of UP is finite. And once the boundary of UP is finite, we know that an open set with a finite boundary can only possess finitely many connected components. So an open set with a finite boundary. So this was only the catch in the problem. You have to check what is the boundary of UP typically. And to be sure about the fact that you are doing the right thing, you should be able to guess this fact that an open set with a finite boundary has only finitely many connected components. or rather whatever you say, open connected components or connected components will do. And because connected components are after a maximal connected subset, so if you have finitely many connected components, then you surely have finitely many open connected components as well. So nevertheless, we are asked about, so option C comes out to be the right answer. Okay, let us move on to the next question. Let me drink some water. So consider the linear map T, which maps polynomials to polynomials, defined by T of Px is equal to the derivative of x times Px. Now I would rather say that this is actually a very easy question. I don't want to spend time in this particular problem, but I'm giving you a hint of how to think of this very problem. What you can actually do is that you can observe something, that if P of x, so you can think of this in the following sense. If P of x, suppose degree of P of x is n. So we are working inside integral domain, so there is no issue of cancelling out coefficients and getting something to be 0 when you are being multiplied by something. So this implies degree of x times P of x will surely be n plus 1, which implies that the degree of the derivative of x times P of x is n. So actually the best way, rather I would say, to solve this very problem is without viewing T as a polynomial over Rx. What you can do is that you can restrict T to polynomials, rather the set Pn, which are the collection of all real polynomials with degree at most n, right? Then the restriction map is also a well-defined linear map because of whatever we did here. And once you subject it to this very set, we know that it's a finite dimensional vector space. So you can be able to admit a matrix of T corresponding to the usual basis, let's say 1x, x squared till x to the power n. And corresponding to the basis, what you can actually do, you can construct out a matrix, and you can check injectivity or surjectivity with respect to the matrix itself. Okay. So this is one approach to this very question. And without restricting it to the finite dimensional subspace, you can also check whether it's injective or surjective by checking what is the kernel of T. Okay, so the kernel should be the collection of all polynomials such that this is exactly 0. For this to be 0, x times P of x has to be having degree 0. And from there you can observe something, that even if P of x is constant polynomial, non-zero constant polynomial, x times P of x will have degree greater than or equal to 1. So the only possible case where x times P of x is polynomial will exactly be 0 should be when P of x is identically 0. There is no other possibility. So the kernel is 0, and therefore this matrix has to be injective. Okay, and the surjectivity is quite obvious, right? The way it's constructed, you can obviously, if you choose an arbitrary polynomial from Rx, you can manipulate the coefficient and construct out a polynomial Px such that the derivative of x times Px will give you the chosen polynomial. So it's actually an isomorphism. So it's actually bijective. But nevertheless, you can also check it, via this very structure, if at all you don't know how to, or rather you are not comfortable with working over infinite dimensional spaces. Nevertheless, let us move on to the next particular question. Okay, so true or false type question. If Px is a complex polynomial which is not equal to 0, then the polynomial P of x minus x divides the polynomial P of x minus x. Now, so let me admit this. I got this question wrong in the exam. Okay, and the reason I got this question wrong in the exam was I chose a polynomial, and then I did a calculation mistake while calculating these two things, and then ultimately I came up with the answer that it might not always divide, but actually it will always divide. And the reason is the following. What you can do is that you can choose Q of x to be P of x minus x, and to check this division, what we actually do is that rather than working over the complex field C, we switch to the quotient field Cx modulo Qx. Okay, now over Cx modulo Qx, it's obvious that P of x minus x has to be 0. So that means that P of x is congruent to x modulo Qx. And this is same as saying that every element divides itself. Okay. Okay. Now see, a polynomial evaluation, as we know that polynomial evaluation, it always commutes with the canonical projection homomorphism, right? Which mapping it to the quotient algebra. Nevertheless, what we actually try to do is that since p of x is congruent to x modulo qx, what we will actually be doing is that we will apply the formal polynomial p on both sides. Okay, because it will ultimately preserve the relation. So therefore, p times px will be congruent to px modulo qx, but px is again x modulo qx. So this implies that qx will divide p times x minus x. And this was exactly what was asked. So therefore it's true. Okay, good question. Let us move on to the next question. So there are only finitely many subsets I of the natural numbers with the property that fx is given to be of the form ai x to the power I, a real polynomial where n is a natural number, and the subsets ai is in q for all I in I, such that this set actually forms a subring. Okay. So how can one typically think about this particular solution? Okay. So the first thing which at least I would rather suggest in this very scenario is to check that what are the possible conditions for this for the set given to us to be forming a subring. Okay, just a minute. So let's move on to the solution space. Okay, so suppose so let us do one thing. First, let us set some notation. So let Ri be the set of all polynomials f of x equal to summation ai x to the power I is equal to 0 to n, where n is in capital N, and then ai is in q for all I in capital I. Okay. Did I do some mistake? I think. Yeah, so this is not something which we have, because we are indexing over this set capital I. So this is not something which we require. We are indexing over the subset of natural numbers, which is I. Okay. Now, firstly observe that if Ri is a subring of Rx, then firstly, 1 must be in Ri. But then 1 is nothing but 1 times x to the power 0. So that implies that the index 0 must be in I. Fine. Moreover, for it to be a subring, it must be closed under polynomial multiplication. And it's closed under polynomial multiplication if the monomials x to the power n, x to the power b, these are closed under multiplication in Ri. So now if these are in Ri, that should imply x to the power a plus b is also in Ri, which should mean that I is closed under addition. So therefore I should contain the additive identity 0, and I should also be closed under addition. What does that typically mean? So therefore, so if you have studied group theory, you know what a submonoid is. So I has to be an additive submonoid of n, rather n union 0. So we can just take it to be n0. Now, how many submonoids can be constructed in n0? You can construct infinitely many submonoids in n0. For example, you can choose the subsets of the form 0k, 2k, 3k, and so on for any k you can think of, for all integers k greater than or equal to 1. All of these will be submonoids. So there are infinitely many submonoids, and if there are infinitely many submonoids, there are infinitely many subsets I. Right? So once there are infinite, so what are the questions saying? There are only finitely many subsets. So yeah, so this is wrong. You can construct infinitely many ones. So this is a false statement. Now I would rather, want to give you a very, very brief hint to the TIFR true or false, and please don't quote me on this. Okay, this is an absolute, sort of a trend which has been followed for most of the TIFR examinations over the years. Most of the statements in the true or false types actually comes out to be false. I don't know why I'm just guessing out this, but I actually feel that about 70% of the statements in the true or false section comes out to be false. And moreover, most of the statements which actually comes out to be false are statements which are framed in the form of there are only this much, there exists only this much, we have only this many things. So these sort of constructions usually come out to be false, because you already have a bunch of examples which will contradict it, and therefore the question is framed in such a way. So if you solve many problems over the TIFR PYQs or the NBHM PYQs, you will develop a sort of a an audio memory in some sense of reading out the question, perceiving it through your ears, and guessing whether it can be true or false. I hope you can understand what I'm trying to say. I may not be able to explain it much, but I hope you're getting it. Again, so this is a very similar question, a sort of a question which I already read. You can do it in the same sense, because if f is a polynomial of degree n, 3f plus 2f prime will also be a polynomial of degree n. So you can just restrict it to n-dimensional vector space and then walk through using matrices. At least that was the way I tried to solve this very problem. But nevertheless, you actually, I wouldn't say you actually need to solve this problem through that perspective, because what you can do that, the thing which is not surjective, it actually can be contradicted by just viewing the fact that whatever polynomial you choose out of Rt, it will be in some sense of some natural form a n x to the power and so on and so forth. What you can do is that you can actually set b to be some b0 plus b1t and so on and so forth. Then calculate 3f plus 2f prime. You set both of their degrees to be same. And then what you can do is then you can just compare out the coefficients to show that you can actually, every time given a polynomial, you can manipulate through the coefficients and construct out a polynomial to prove that L is actually surjective. And moreover, if we actually try to restrict it to the n-dimensional polynomial, you will see that the matrix, the corresponding matrix, will be an upper triangular matrix with non-zero diagonal entries. So it has to be surjective, obviously. So this is a very easy exercise. You can try it on your own. Without wasting our time, let us move on to the next question. Okay, so what is it actually given to us? So X is the collection of all tuples BC in R2 such that the polynomial x square plus bx plus c has distinct roots in C. It's connected. Okay. Now when does a polynomial have distinct roots? Okay, we know that a polynomial, a genetic quadratic polynomial x square plus bx plus c in Cx has distinct roots. Over C we are speaking if and only if the algebraic discriminant, which is b square minus 4c in this case, this is non-zero. So therefore the set X which is given to us, it is exactly the inverse image under the discriminant of R minus 0. Okay, clear? Now observe that, so what is R minus 0 typically speaking? So it is just minus infinity to 0 union 0 to infinity. Okay. And under inverse images, we know that unions split. So this is just of the form, minus infinity to 0, union infinity, 0 to infinity. And now this is open, this is open. Delta is a continuous function, so X has been decomposed into two disjoint open sets. And once a topological space is decomposed into disjoint union of open sets, it's by the definition itself, it has to be naturally disconnected. So therefore this space is not connected. So it's basically disconnected. And it's a false statement. Clear enough? Let us move on to the next question. Okay, so we are done with all the questions. Nevertheless, I hope you like this very lecture. Let us move on to the get back to the first page. So this is your JSG Maths Excellence Academy, and we just finished with the advanced ring theory problem session, particularly focusing on the TIFR PYQs. In the next session, we will be bringing up PYQs of the NBHM exam, and once we are done with that, we will solve some miscellaneous problem sets. Nevertheless, I hope you like the video. Please do like, share and subscribe to JSG Maths Excellence Academy. Meet you guys in the next lecture. Please stay tuned. Bye.